Let's explain everything is going to discuss the ionic basis of the cardiac action potentials. Remembering that there's two different types of action potentials that we have to look at. We have to look at the autorhythmic cells and we have to look at the myocardial contractile cells. The autorhythmic cells are also known as the pacemaker cells, and these are the cells that are going to be found at the SA node, and these are the cells that are going to be responsible for regulating the heart rate. The myocardial contractile cells, these action potentials are going to lead to muscle contraction, and so these are going to be underlying the mechanical events of the heart, okay, the actual cardiac muscle contraction leading to systole in the atria and in the ventricle. Let's start by looking at the autorhythmic action potential. So we're going to be looking at the membrane potential over time. So we're going to have the change in membrane potential in millivolts and the time in milliseconds. So the thing to note here is that the resting membrane potential never rests. So what the cells do is they spontaneously depolarize. So here around minus 60 millivolts, it is going to depolarize till it reaches a threshold and generate an action potential, comes back to minus 60, at which point it will again spontaneously depolarize and generate another action potential, and the story will continue. So now let's take a look at what is responsible for this part of the action potential. And again, it's not a resting membrane potential because it never rests. This is known as the pacemaker potential. And if we take a look at it, we realize that this is a depolarization, which means that the inside of the cell is getting less negative. And if we have the inside and the outside, okay, which means that the inside is getting less negative, which means positive charge must be coming inside the cell. So again, inside, outside. If this is becoming less negative, positive charge is coming in. We have two possibilities for positive charge. There are two cations that are highly concentrated on the outside of the cell, and that is sodium and calcium. So either of these could be coming in and making the inside of the cell less negative, therefore causing depolarization. The question now is, which one is it that's responsible for the pacemaker potential? The answer is both of them. Okay? The initial depolarization coming from the minus 60 is going to be due to sodium, and then the second part of the pacemaker potential, just finishing it up at the end, is going to be due to calcium. So at minus 60 millivolts, there are specific channels in the pacemaker cells, the autorhythmic cell membrane, that are going to open. So these are going to be voltage gated channels. And what happens is as they open, sodium will come in through those channels. Okay? These channels are known as the IF channels, because they are so funny. Again, I do not lie. That is why that channel is called the IF channel. So that accounts for the initial depolarizing phase of the pacemaker potential. Okay? Those channels close, which then opens up the voltage again. Is going to open up voltage-gated calcium channels, and calcium will come in to the cell. Okay, this is then going to account for the second part of the pacemaker potential, bringing it to threshold. Upon reaching threshold, we then generate the upstroke of the action potential. This is due to, again, cations moving in to the membrane, making it less negative, depolarizing it. But unlike our neuronal action potential where that would have been sodium moving in, this is going to be, again, due to calcium moving in. Just noting that the calcium channels responsible for the upstroke are different than the calcium channels required or that are opening during the last phase of the pacemaker potential. After the depolarizing phase, which if you note is reaching about 10 millivolts, positive 10 millivolts. So there is a switch in the polarity. Not as great as the neuronal action potential, but I'm not even too concerned that you know anything about those numbers. Okay, all I want you to appreciate is that as the calcium channels, the voltage-gated calcium channels are closing, okay, the potassium channels would have already been opening up just like the neuronal action potentials, but they're slow. So once they are opened up, now they are going to cause the repolarization, and it actually goes back down to minus 60 millivolts. So again, if we just take a look, we have the inside and the outside. What we are now doing is making the inside of the cell less positive, and that is because potassium, okay, is moving out. So the repolarizing phase and the actually going down to the minus 60 is due to the potassium moving out through, again, voltage-gated potassium channels. So in summary, the initial part of the pacemaker potential is due to sodium moving in through those IF channels. The second part of the pacemaker potential is due to calcium moving in through voltage-gated calcium channels. The upstroke is due to calcium moving through voltage-gated calcium channels, different than the original ones. The downstroke is due to potassium moving out, and at the point where it reaches the minus 60, the potassium channels will have closed, and once again, these voltage-gated IF channels will have opened up and start to depolarize again, and the next action potential will be generated. So now we generate another action potential, and this process is going to continue again and again and again, appreciating the fact that the frequency of these action potentials is going to be the underlying cause and regulating heart rate, because this is the pacemaker, it's coming from the SA node, it is at the beginning, it is the highest frequency, which is going to be controlling the spread of electrical activity through the rest of the cardiac conduction system. As mentioned previously, the rate of these action potentials underlies the rate of the heart beating, so the heart rate. So let's just take a look here. Say we have a normal heart rate and it is going to be depolarizing, reaching threshold, generating an action potential, depolarizing, reaching threshold, generating another action potential. If we want to increase the rate of the heart, we are going to have to increase the rate at which it reaches threshold, or increase the rate of depolarization. If we do that, we are now going to be generating action potentials, okay, at a faster rate, and therefore increasing the heart rate. So the question is, how is it that the rate of depolarization can increase? In order to increase this rate of depolarization of this pacemaker potential, we can alter the movement of sodium in through these IF channels or the calcium in through the voltage-gated calcium channels. The increased rate of cation movement inside the cell is going to increase the rate of depolarization. So the question is, what can increase the inflow of these ions through these channels? The answer is epinephrine and norepinephrine. Remembering that the norepinephrine, as we looked at last term, is a neurotransmitter released from the sympathetic nervous system. So that makes sense that the rate of depolarization increases, increasing the rate of action potentials, increasing heart rate, and that goes along with the fight or flight response. These autorhythmic cells have receptors to epinephrine and norepinephrine, and these receptors are the beta 1 receptors. And this is going to come into play when you get into pharmacology. To decrease the heart rate by decreasing the rate of these action potentials, we want to decrease the rate of depolarization so it is taking a longer time to reach threshold. Okay, what happens is the potassium efflux, okay, out of the cell is increased and the cell actually hyperpolarizes. So now it has a further distance to go to reach threshold and is going to decrease the rate of depolarization. The other aspect that is affected is this calcium channel. The end result is that you have a longer and slower rate of depolarization and therefore decreasing the frequency of the action potentials. The neurotransmitter that does this is acetylcholine, and this is being released from the parasympathetic nervous system, and that makes sense because fight or flight, rest or digest, the parasympathetic nervous system is going to decrease heart rate. Remembering that the acetylcholine is binding to cholinergic receptors, and at the SA node, these autorhythmic cells have muscarinic receptors to which this acetylcholine is binding. Muscarinic. Now let's take a look at the myocardial contractile cell action potential. First of all, what I want you to appreciate is the duration of these two action potentials. The previous autorhythmic action potential was around less than 1 millisecond in duration. Okay, so please appreciate here that the duration of this action potential is in the realm of 250 milliseconds. So it has much longer duration than the autorhythmic action potential and the neuronal action potential, which is again was around 1 millisecond. So if we look at this now, we're going to see that it does indeed have a stable resting membrane potential of around -90. Okay, and then we are going to see the various phases of the action potential. There is going to be a very quick upstroke. Okay, and this is again is going to be depolarization. And then the cell starts to repolarize. Right here, it's going to start to repolarize, but then it all of a sudden plateaus. And this plateau right here is what's going to extend the duration of the action potential to around 250 milliseconds. Okay, it then continues to repolarize and will be going back down to the resting membrane potential. So let's take a look at what ions are responsible for all of these components of the action potential. And let's start with the rapid upstroke. Okay, the rapid upstroke of the action potential is due to sodium moving in through voltage-gated sodium channels. The cell starts to repolarize, as you can see right here, and that is due to potassium moving out of the cell. However, very quickly, voltage-gated calcium channels are going to be opened up. So calcium channels open up here, and calcium is going to come in and offset that potassium moving out, and as the calcium comes in, it is going to maintain that level of depolarization, accounting for the what's known as the plateau of this action potential. Okay, and that is this section right here. So then what happens is the voltage-gated potassium channels open up and the calcium channels close, so now the efflux of the potassium out of the cell causes the cell to repolarize back down to the resting membrane potential. So now the question is, what is the significance of this extended plateau of increasing the duration of this action potential? Remembering these are the myocardial contractile cells, and it is these action potentials that will be triggering the mechanical contraction within these cells. Now let's just remember what a refractory period is. For this action potential, okay, the refractory period is going to be the duration of that action potential. So the absolute refractory period here is around 250 milliseconds. So we have a much longer period during which another action potential cannot be stimulated. We have to go back to a concept of muscle contraction a little bit here just for a minute and look at, say, that this is contraction, relaxation, contraction, relaxation, contraction, relaxation. In skeletal muscle cells, what happens is if there is another stimulus before the muscle has relaxed, you will increase another stimulus, increase another stimulus, increase until you get to the point of what is known as tetanus. This is sustained contractions in skeletal muscle. You have to appreciate that in cardiac muscle, it must relax and then contract again so that the heart can fill with blood. Okay, so this relaxation phase here is important so that the heart can fill with blood and therefore be pumped. So the reason that we have this extended action potential is so that the duration of the action potential actually is exactly the same as the contraction relaxation cycle of cardiac muscle. Which means, because of the refractory period, we cannot generate another action potential until that cardiac muscle cell has relaxed. So this evolved to prevent tetanus in cardiac muscle.